Class, we'll start with IUPAC nomenclature for coordination complexes. Class, it can be studied under three heads: naming cationic complexes, naming anionic complexes, and naming neutral complexes. Class, first heading is naming cationic complexes. So we should know what are cationic complexes. If coordination sphere bears net positive charge, for example, and positive charge called cationic complex. Cr ammonia 6, Cl3. If I dissociate, it gives me 3 chloride, Cr ammonia whole 6 and 3 positive. Class, while writing IUPAC nomenclature, you must have to find out the oxidation number of Cr. So how to find out? Let us take Cr equals to X. We all know ammonia has no charge, so 0 into 6, and this must be equal to plus 3, so the value is coming plus 3, and it's a cationic complex. So class, whenever we are going to name a cationic complex, see the rules. Cations are named first, followed by anions. For example, if it is written KCl, we always call it potassium chloride. So we are naming cationic part first, potassium, followed by chloride. Similarly, in this case, the cation will be named first, followed by anion. Second, MgCl2, AlCl3, class, what do we call it? We call it magnesium chloride, aluminium chloride. We never say magnesium dichloride or aluminum trichloride. Similarly, in this complexes, we are not going to say trichloride, because this 3 represents the valency here. So it is the charge over here. So whatever the name is going to come, it will simply carry chloride. It will never be called trichloride. Point number 3. While naming cationic complexes, this is a coordination sphere, so we will have to name them first. So class, remember always, legends are treated as guests because they are going to come and they are going to give us lone pair. Therefore, they are always given priority. So while naming cationic coordination sphere, legends are named first. Legends are named first. So you are going to tell about legend first, then central metal atom, then CMA. So class, I repeat the rules again. Cations are named first, followed by anions. I have given you an example, KCl, potassium chloride. Then if you get a formula like this, Cl3 or Cl4 or Cl5, we are not going to write trichloride, tetrachloride or pentachloride. We simply say chloride, as we have been doing. See, MgCl2, we are simply saying magnesium chloride. We are never saying magnesium dichloride. Similarly, AlCl3 is always said aluminum chloride. It is never said aluminum trichloride. So while writing their name, it will be also not called trichloride. Remember it, very, very important. Then point number 3, while naming cationic coordinations here, legends are named first and then CMA. So that was the rule number 3. Now rule number 4. Legends are named as per their alphabetical order. Alphabetical order. Amine is preferred over aqua. How class? Okay, amine you know ammonia, aqua you know water. So it is being said that amine is preferred over aqua. The reason is that you see in the first point of difference should be taken, both are containing A, but in the second step it is containing M and it is containing a Q, so it is more alphabetically superior. So that's why amine will be preferred over aqua. So while writing their name, you should be following alphabetical order. Okay, we'll continue here only. Alphabetical order. This is a bracket followed by name of central metal atom in parenthesis. Central metal atom with oxidation number. With oxidation number in parenthesis. Parenthesis means chota bracket. So first you will name legend, followed by central metal atom along with its oxidation number in parenthesis, followed by anion. So let us name this one. Cr ammonia 6 Cl3. We have already calculated oxidation number of chromium as plus 3. So cationic part will be named first. In cation we are getting two things. I have already told you coordinations here will always contain two things, legend and central metal atom. We are supposed to prefer legend, and legend is ammonia. How much? 6. So you see the name hexamine, and class there should not be any gap. Hexamine, chromium C should be chota. Chromium, and then followed by oxidation number in parenthesis, and then finally chloride. So this is the way you can write the name of cationic complex. First, you tell about the cationic entity. In cationic entity, we are getting two things: legend followed by central metal atom. Legend is ammonia, 6 ammonia, hence the name hexamine, chromium 3 chloride. See this hexa, this is a prefix. Prefixes such as di, tri, tetra are not considered for alphabetical superiority. Let us take one more example. As usual, first find out oxidation number. Class, if it is -2, it must be having +2 charge here. So let us find out chromium X, ammonia 0, nothing to write, water 0, nothing to write, but chloride is -1, and this must be equal to +2. So in the next step, we get X equal to +3. So the chromium is sitting here at oxidation number +3. Now we have three legends. Class, we are going to name this cationic entity first. We all know first the legend will be told, and then central metal atom will appear. This is amine, this is aqua, and this is chlorido. Amine, will be followed by aqua and then followed by chlorido. Class, see how I'm writing the name. Triamine, then diaqua, then chlorido. See, no space is being left. Chlorido, chromium 3 chloride. So class, though prefix contains the word T, we are not going to take T, D into consideration. We'll simply see the name of the ligand. It is amine, it is aqua, it is chlorido. So amine will appear first, followed by aqua, followed by chlorido with their prefixes. Hence the name triamine, diaqua, chlorido, chromium 3 chloride. If the name of ligands itself contains the word di, tri, tetra, in such situations, special prefixes are used. Special prefixes are used. What are those? For 2, we write bis. For 3, we write tris. And for 4, we write TTRA. TETRAKIS. So for 2 we write bis, for 3 we write tris, and for 4 we write TETRAKIS, that is tetrakis. So these are special prefixes. How they are used, I am going to take you one example over there. Class, this is a coordination complex containing sulfate as anions and ethylene diamine as a ligand. And ethylene diamine, how many ligands are there? There are 2 ligands are there. So first find out the name of the ligand. The name of the ligand is ethylene diamine. So in the name of the ligand, the word di is there. Therefore, in such situation, we will use the special prefixes. So how many ethylene diamine are there? There are 2 ethylene diamines, so we'll use the word prefix bis. And let us find out here what is the charge on this cationic complex. If it is -2, then cationic complex here charge is +2, and since ethylene diamine is neutral, so oxidation number of copper is 2 here. So class, let us see how to write. First we are going to tell about ligand. Ligand is how much? Twice. The special prefixes bis ethylene diamine. Continuation, copper 2 sulfate, and class, you must see that the name of the central metal atom is always in small letters. You see, chromium is small letters. Hexamine again, chromium is small letters. Copper is again small letters. So you will be writing straight line, no gapping, and the name of the central metal atom will be appearing in small letters. So that was all regarding your naming of cationic complex. Let us take one more. So class, let us take one more example here. FeH2O whole 4, Cl whole twice, and then Br. As it is a cationic complex, the reason is that if Br is -1, then this coordination here is +1. That's why it's a cationic complex. Now let us find out the oxidation number of iron. X. Class, you all know water is neutral, so no, neglect water. 1 chloride has -1 charge, so 2 chloride -2. This must be equal to what? +1. In the next step, I get the value +3. So iron is sitting here at 3. Now we have 2 ligands over there. One is your aqua, other one is your chlorido. So I will start with aqua. How many aqua? 4. Tetra aqua. dichlorido iron, 3 bromide. So this is the way to write down cationic complex nomenclature. So class, now we are going to take the second one, naming anionic complexes. So the class heading is naming anionic complexes. What are anionic complexes? Coordination sphere bears negative charge on it. They are called anionic complexes. Let us take one example here. K4FeCN whole 6. So class, we all know potassium, one potassium carries plus one charge, so 4 potassium will carry 4 positive charge. So if potassium carries 4 positive charge, then coordination sphere is going to carry minus 4 charge, and since it is carrying minus 4 charge, that's why it is called anionic complex. Now class, rules, same thing, cations are named first, followed by anions. Cation will be named first, followed by anions, but before going to that, let us again take some examples. Now let us consider these three compounds. What are their names? Sodium oxide, we never say disodium oxide. Magnesium oxide, aluminium oxide, we never say dialuminum trioxide. So these 2 and 3, they are representing the valency of the crisscross valency of the other element. That's why we will simply say sodium oxide, magnesium oxide, and aluminum oxide. Similarly here, whenever we are going to start, we will never say tetra potassium, we will simply say potassium, because this 4 represents valency of this coordination sphere. So first of all, you'll tell about this, then cations are named as followed by anion, and number 2, while naming anionic coordination sphere, again legends are named first as per alphabetical order, as we've been doing, followed by CMA with its oxidation number in parentheses, but the name of the metal ends with suffix 8. This is the basic difference between cationic and anionic. Here, the name of the metal will end with word suffix 8. For example, iron becomes ferrate, nickel becomes nickelate in all anionic complexes. Cr becomes chromate. So we'll have to use suffixes 8 during the naming of the central metal atom. So class, let us try here. But before we try, we should know the oxidation number. So Rnx, class, we all know one cyanide is -1. So -1 into 6 equal to -4. So this gives me x, -6 equal to -4, x equal to, I am getting +2. So oxidation number of iron is +2. Class, I have already told you I am not going to write tetra potassium because this 4 is showing the valency of this. So we'll simply write potassium. So cationic part over. Now we'll move to anionic sphere. In anionic sphere, again legends are guessed, so they will be preferred first. So hexacyanoferrate 2, potassium hexacyanoferrate 2. That becomes your expression for nomenclature for this complex. Potassium hexacyanoferrate 2. Let us take one more example. So class, if potassium is plus 3, then this will contain minus 3. That is not oxidation number of iron. X. For chloride, I can write minus 2. For bromide, again I write minus 2 because 2 bromide and 2 chloride is simply 2 iodide. So minus 2. This must be equal to what? Minus 3. So x minus 6 is equal to minus 3. X equal to plus 3. So iron is sitting here at plus 3. So the class, the name becomes, first we'll write potassium. Then we have 3 legends: chlorido, bromido, iodido. So bromido will appear first. Potassium dibromido, dichlorido, diiodido. Continuation. Ferrate 3. So this word 8 will tell us that the complex is anionic. So during anionic complexes, central metal atom always ends with word 8. So class, all the other rules remain same. Now that prefixes are not taken for consideration for probability superiority. If we are getting special prefixes having the name di-, tetra, the word in the name of the legend itself, then we'll be used this case as we have been doing. So we have taken 2. First we have taken cationic complex. Now we have taken anionic complex. Now we will move to neutral complex. Naming neutral complexes. Naming neutral complexes. It's very easy. Let us simply write NiCO whole 4. Class, what do we find? We find that complex is neutral because CO has no charge. Neither anything here nor anything there. So it's a neutral complex because CO has no charge. So Ni also has no charge. So the charge on them is simply 0. That's why they are called neutral complexes. Now we have only to name these coordinations here. No one here, no one there. And we all know that whenever we are going to name coordinations here, legends are preferred first. So class CO is called carbonyl. The name becomes tetracarbonyl nickel 0. So here we are not going to use word 8. 8 is only meant for anionic complex. For cationic and for neutral complex, there is no characteristics ending called 8. And now the last topic becomes naming bridging complexes. So naming bridging complexes. Some ligands act as bridge between two CMAs, central metal atoms. Therefore, prefix mu is used before them. Let us take example. So class, this is your bridging complex. We find that there are two groups, two ligands which are acting bridge between this iron also and that iron also. So they are called bridging ligands. And whenever we are going to write their names, bridging ligands, we will be using prefix mu. But before we move to naming them, we should know what is NH2. Class, remember ammonia was called amine, and if you replace 1H positive here, you get NH2 negative called amido. Take one more out, then 2 negative charge appears called imido. Take one more H out, so it is called nitrido. But here we are going to use amido and it has -1 charge. So class, water has no charge. One sulfate has -2, so both the sulfate has -4 and -4 will be balanced by +4. Let us find out the operation number here. Iron 2x plus -1 because we know hydroxyl has -1 charge. Amido also has -1 charge. And this must be equal to what? +4. So 2x minus 2 equal to +4. 2x equal to 6. So x equal to +3. So both Rn are sitting at 3 here. Class is a cationic sphere. So the legend will be told first. How many legend? 4. Class, I am going to write the name. See, very easy. Tetra aqua. Iron 3. This is amido and this is hydroxyl. So amido will be alphabetically superior. Mu amido, mu hydroxyl. Again tetra aqua. Tetra aqua. Both A will be there. Tetra aqua. Iron 3 sulfate. So this is the way to write bridging complexes. I repeat again. Tetra aqua, iron 3, mu amido, mu hydroxo, alphabetically superior, mu amido, mu hydroxo, tetra aqua, iron 3 sulfate. So class, we have taken all nomenclature of coordination complexes. First we took cationic, followed by anionic, then followed by neutral, and now we have completed bridging complexes. So next topic will be valence bond theory.